So, Alex, we can get started now.
Okay. All right, can you see this?
Yes, go ahead.
All right, well, welcome everyone to day 2. So today we're going to get into research frontiers. And so really quick, let me just remind you of our some of our goals in neurosymbolic. So one, this again is something I made up as an acronym, but to get across the idea of interpretability, and of course, I think the applicability is that the symbolic part of neurosymbolic can be human understandable, and also a way to add knowledge and constraints. Learning with less, why? Because you're effectively, one reason is we could effectively add another resource, which is knowledge, in addition to raw data. And finally, out of distribution generalization. Why? Potentially because of adding reasoning, which can chain things together to a point where you can leave the realm of directly experienced raw data. Okay, now we're going to have deliberately curated some diverse approaches to show you today. You've effectively seen some approaches already yesterday, but they differ in that, for one thing, if you go to the lower left picture, emphasizing different aspects within the neuro, in quotes, and symbolic sides. And I'll just mention one thing. So probabilistic graphical models I've written in the learning side, because that's typically where it lives, but can also be seen as a symbolic representation, of course, on the other side. And you in particular be seeing some approaches that look at causal graphs, so as a form of probabilistic graphical model. So, and I wish we'd talked about that yesterday, but the next time we can have that in the tutorial part. Now, one other kind of an axis is tightly coupled versus loosely coupled representations, or you could say 1 versus 2 representations, and distributed versus disentangled. So I think, and we'll come back to all of these things in the panel at the end of the day. Just a reminder for speakers to leave 5 minutes for Q&A. Asim will jump in and remind you. For the audience, please use the Q&A section as opposed to the chat. That's where we'll look for questions. And everything will be viewable on the webpage afterward. Okay, and with that, let me introduce our first speaker. So Naoki is a distinguished research staff member at IBM and former adjunct professor at Tokyo Institute of Technology. In addition to being a joy to work with, among other things, he has contributed significant results in learning theory, such as on the hardness of learning grammars, temporal causality, and sequential decision-making. Over to you, Naoki.
Thank you, Alex, for the kind introduction. So let me share my screen. Do you see my screen now?
Yep.
Okay, let me put it into the slideshow mode. Okay, yeah, so yeah, thanks for the introduction. I'm really more of a machine learning person, but I've worked on pack learning theory of Leslie Valiant when I was much younger, and I've always been interested in the subsequent development by Leslie on combining learning and reasoning, sort of extending the packed learning paradigm. And more recently, under Alex's supervision, we've started sort of building on that work and trying to do more application and some extensions. So we're happy to report on some of those progress in this opportunity. This is joint work with Ryan and Alex, and also with significant help from Marlon, Olga, and Parik, and others actually who have been joining the discussion and so forth. So thanks to them for this opportunity. So here's the agenda for the talk today. I'll start with introducing some motivation and extensions for robust logic. For those of you who listened to Leslie's lecture yesterday, some of this could be redundant, but I'll briefly review the basic elements of robust logic. And then I'll talk about some applications that we have started working on of robust logic. And then a couple of extensions of robust logic that we have started working on. And then I'll talk about some benchmark experiments for those applications and extensions, and we'll conclude the talk. Okay, so first, motivation and extensions. So the first motivation of robust logic is that we want to integrate learning and reasoning with guaranteed efficiency and correctness. So I think this is very important in today's environment, especially as something to complement deep learning, to provide factuality and accountability. Additionally, this approach also allows you to do small sample learning, which also is important, especially in enterprise application scenarios in which we may lack the luxury of having internet scale data availability. And besides, this framework provides enough descriptive power and reasoning capability to perform comprehensive reasoning, in which we may leverage the domain knowledge. So these are the main motivations. And some key properties of robust logic include that there is a guaranteed learning efficiency in the style of packed learning. There's also guaranteed reasoning efficiency, which Leslie called packed soundness for the reasoning or deduction part. And overall, this approach sort of presents you with a flat structure of relatively rich expressions, which are both learnable and also admit reasoning. Some desirable extensions, some of which we have started, include to have a wider class of logic with efficient learning and reasoning, extension to real valued logic, and to leverage some of the modern learning technology to allow more sort of richer computational approaches towards this within this framework. Okay, so some review of core elements of robust logic very briefly. A rule in robust logic takes this form, where you have this predicate Q, which is called preconditioner, which sort of divides the world into a finite number of subsets, and in each there are a number of rules that define relations in terms of some logical gate function defined over what he calls independently quantified expressions. So here's a concrete example where for the Boolean function f, it's potentially any arbitrary Boolean function, but mainly in his original work, he restricted this to be linear threshold gates. So this is a typical example of such a rule where it's universally quantified upfront, but within this threshold gate, you have some independently quantified expressions of this form. It's interesting to note that the linear threshold gate subsumes both disjunction and conjunction and things that are in between. And we could potentially build up more complicated expressions by chaining multiple rules. For example, if we're going to define a hybrid notion like grandfather, in terms of atomic relations like father and parents, you could define it with a single rule like this. But in the original formulation of robust logic, this kind of composite independent quantified expressions were disallowed. For this, you can achieve the same thing using multiple rules. Also, alternatively, you can relax this constraint and have sort of composite IQEs, allowing to have this kind of relation expressed in one single rule as well. So a very notable property of this version of robust logic that Leslie presented is the efficient learnability. And so not only that this class of robust logic restricted to threshold gates is pack learnable, it's actually learnable with very, very small sample and very sample efficiently. And this is made possible by a classic result of Littlestone using the learning algorithm called WinOut, which actually can learn R of k threshold functions over n variables with sample complexity of this order, which is linear in the number of relevant variables, but it's logarithmic in the number of irrelevant or total number of variables. And this contrasts starkly with similar algorithm for learning linear predictors and like perceptron, where the dependency of sample complexity of perceptron is linear in n. So here's a graph that contrasts the sample complexity of WinOut and perceptron, where if you double the number of irrelevant features, the number of mistakes made by perceptron doubled, but the number of mistakes made by WinOut only increases slightly. So this is a very important aspect of the core of robust logic that we will see in action later. The other, the counterpart of this is the efficient deduction. As Leslie mentioned in yesterday's talk, with packed learning guarantee on the learning side, you can also guarantee packed soundness of a certain general deductive algorithm for robust logic. I will not go into detail in this talk, but you can refer to his paper from 2000. So I will now describe some applications of robust logic. The simplest one and the one that we will focus on today is tabular data classification. It's really a classical machine learning problem, but we will see how robust logic does with this classic and simple task. We're engaged in a number of other somewhat more complicated applications, including time series classification, via temporal extension of robust logic, and also integrating causal modeling with robust logic, applicable to AI ops and other domains. It's also applicable to things like grammar induction and compositional reasoning, such as the ones that Sohan, Dan, and Parry yesterday were talking about. So overall, robust logic is a rich and general framework that enables a wide range of application scenarios. But today, so I will talk mostly about the tabular data classification. But how is it possible to apply robust logic to these, varied application scenarios? And that's done through something called scenes, which Leslie talked about yesterday. So what is a scene? Basically, the scene consists of a number of objects or tokens in the world. And the scene provides a vector that states for every relation under consideration and every variable bindings over the tokens, whether each relation holds for that binding. And by appropriately defining these scenes, you can apply robust logic to many different kinds of application scenarios. So here's a little bit of more detail of how this scene works. If you have a number of objects and you have a number of relations, these are the independent quantified expressions that go into the rules. Then basically you need to provide, a scene will need to provide the truth values for various bindings such that the truth values of these relations can be evaluated. And the problem of learning the definition of a given relation in terms of other quantified expressions can be reduced to a Boolean learning problem. And any Boolean learning algorithm can be invoked. But for tabular data, these bindings can maybe restricted to just map to specific columns of the tabular data for unquantified relations, but they may have to map to arbitrary columns for quantified relations. So we'll see some examples of this, but this just goes to say that you may not have to consider all possible bindings depending on how the application is set up. For event data, the tokens may map to events. But for tabular data, they typically map to columns in the thing. So here's an example, simple but concrete example of a tabular data, the iris flower data, which is very simple. It only contains 4 columns or features and a class label. It's very small in terms of the number of examples as well. And the robust logic rule that we want to learn will express the class in terms of relations over these features. So you may have unary relations like this one, where it says basically this variable is the first column, and it's less than 0.5. For this kind of specific unary relations, the bindings can map to a specific column. But for quantified unary operators, like there exists a variable such that it's less than 0.5, then these variables will need to map to arbitrary columns. You can have binary relations, for example, that the F1 feature F1 is less than feature F2. For this kind of relation, the variables will map to specific columns. You may have also have quantified binary relations, where you might say there exists some column such that x1 is less than that column, and for those for such a quantified variable, the bindings will have to map to arbitrary columns. So here's an example result of applying robust logic learning to this tabular data using these sort of varieties of relations. So if you have unary features only, this data with only 4 columns map to something like 100 features, and you can obtain classification accuracy on 93%. But by using richer and richer relations, like binary features and quantified unary features and so forth, you can get up to 98% accuracy. And you can learn some logically interpretable rules of this form. For example, using binary relation, you can learn this type of rules where each class is defined as a threshold gate in terms of this type of relations which sort of capture separating hyperplanes, in this case restricted to binary relations. Potentially you can have thousands of different relations from which, thanks to the simple efficient learning of ReNAL, you can quickly learn rules consisting of a small number of relations. And this is an example using quantified unary relations, where you can have more succinct rules using this kind of quantified relations as well, achieving very good accuracy in this case. Okay, so that was an example application to tabular data. I'd like to go into some extensions of robust logic that we've been working on. One is extension to real-valued logic, and the other is the extension to include the learning of preconditionals, the predicates that we looked at, that divide the world into a finite number of subsets. So first, real-valued logic extension. We'd like to now generalize so that these predicates, both the Q and R, they now take continuous values between 0 and 1. And so do these independently quantified expressions. And potentially, we may have to clump the values using like the Leroux kind of clumping. However, for this extension that we've been able to do for now, we require these weights to be simplex, meaning that they're non-negative and sum to 1. And in this case, you actually don't need the clamping. The values stay within the 0-1 interval. And for this class of weighted sort of linear real-valued logic, you can show that using the exponentiated gradient algorithm, which sort of is a generalization of the ReNAL algorithm, you can learn this class of logical rules with also a logarithmic sample complexity, where n is the total number of values. And as many of you may be aware, the exponentiated gradient algorithm is an online algorithm, which is sort of like Perceptron, except the weight update rule involves exponentiated gradient, and it's derived by minimizing the loss incurred in the current trial and the distance between the updated weight and the current weight. And depending on how you define this distance, you derive different algorithms, either perceptual or exponentiated gradient. And the exponential gradient is derived when you use the relative entropy as the distance between these weight vectors. The actual algorithm is simple, but it updates the weights in each trial, where this update involves an exponential of the loss of the current trial. And as a remark, if you use the squared loss in terms of this for this distance, then gradient descent of perceptron is flat. So using this exponential gradient algorithm, and essentially as a corollary of theorem by Kivinen and Varmuth, you can show that this algorithm can learn this 0 valued extension, the continuous valued extension of robust logic with simplex weights with sample complexity, which is logarithmic in the total number of variables. So this is an encouraging theoretical account of this extension. We will see some of that in the benchmark experiments. The other extension that we've worked on is that we want to learn these preconditions. In Leslie Berlin's paper, he didn't necessarily talk about learning these preconditions, but we would like to learn them from the data. And in particular, we would like to do that through boosting, so that in the end, you have a mixture of rules with these Q weights where you can predict with higher accuracy, but we can devise a sort of a local explanation given that ensemble, so that for any particular example, you can point to a single rule within the ensemble having the maximum Q weight. And the way we propose to do this is by leveraging the individual boosting weights in the boosting algorithm. If you recall how the Eta boost algorithm works, the individual weights for the examples in the training data get updated depending on whether mistakes are made on each of those examples. And but in the final ensemble hypothesis, those weights are not made use of, but only weights for the models are used. But here, we're proposing to use these individual boosting weights for the sake of local explainability. Maybe we won't have time to go into the details of how this mechanism works, but it's essentially, given the truth value of any given test data, you can recover how the boosting weight for that example would have been updated through the training process to determine the individual example weight for that test data. And this is sort of a counterfactual explainability scenario, but this is indeed applicable when we are talking about deduction, because you want to prove a certain truth value, the backward proof would actually involve known truth values. So this would be applicable. And here's some examples of boosting experimentation where the accuracy goes up, and for the obtained ensemble, there is a particular model with minimum training error, which you might use for the global explanation, but this mechanism can point to different model for each example through this local explainability mechanism. So I'd like to then finally show some results of benchmark experiments. We've chosen to select some small data sets from OpenML. And this is because we're sort of targeting small sample scenarios. And with this kind of criteria, we can filter over 20 data sets. This is sort of preliminary. Using these roughly 20 data sets, we are able to sort of evaluate what sort of classification accuracy we can obtain.
So, Naoki, can I request you to please wrap up?
Okay, I'll be wrapping up. Yeah. So as compared to these 10 baseline algorithms, including nearest neighbor, random forest, neural net, and so forth, these variants of robust logic are competitive. The version with Rhino is sort of comparable. The one with the exponential gradient improves over that. And finally, with the boosting put on top of it, it sort of becomes the state of the art, exceeding all these baseline algorithms. And here's some scattered plots for each pairs of these comparison algorithms, where you can see that the boosted version of robust logic actually overtakes neural networks and the popular XGBoost. All right, so to wrap up, in this talk, we reviewed the robust logic, and we've introduced some preliminary efforts we're making in some applications. We've discussed some extensions of robust logic, and in the future, we'd like to continue to explore and experiment with a wider range of applications, and as well as solidify both theoretical and empirical foundations of robust logic over 6 stations. Thank you. Sorry for taking more time than I should have. Let me stop here.
Oh, thanks, Naoki. That was great. And sorry, I ate some of your time. So that eats into our question time. But just a few things. So I'll paraphrase a few comments. So what about Ross Quinlan's C5 algorithm for supervised learning from tabular data by automated ML rules?
Yeah, so it wasn't necessarily included here, but we've run some experiments, and C4.5 would have inaccuracy probably around here in the 70% region. So also it's the model tends to be bigger with decision trees. So even though it's in theory interpretable, it gets more complicated, I guess.
One more quick one. Is robust logic only based on learning rules, or can you also mix crafted ones that will be extended by the learned ones?
Yes, that's a good question. And yes, the idea is indeed that you can mix in rules coming from domain knowledge. And I think in Leslie's work with his former student, they've done that kind of thing. And we also are trying to use robust logic to integrate different kinds of knowledge, not only rules that are learned in this manner, but also, for example, rules that are learned from causal, modeling. It's a general framework that allows you to integrate different sorts of knowledge, which I think is one of the strengths of this framework.
Okay, great. Thanks so much, Naoki.
Okay, thank you.